Hi, welcome. Nice to see a lot of familiar faces here. I decided to start right on time now, although usually I start a little bit late because I don't know what time it is. I just checked out and found out it's time to start. The reason is on Saturday I was thinking, hey, I've got to give a talk next Wednesday, and I'm not sure I know enough stuff to say that'll make the lecture interesting. So I started working on this topic of lattices of trees, and now I got the opposite worry. I think I've got too much to do. So I'll just tell you what, as much as will fit in the hour comfortably, and if there's anything left over, well, there's always another Christmas coming up later. This is the fifth year in a row that I've given a lecture just before the end of the winter quarter about trees. So we call it the Christmas tree lecture, and in some ways trees are about the most interesting thing in computer science, or at least let's say computer scientists love trees more than anybody else, and even poets love trees. So I don't know how many years I'll be able to go on with something really interesting new about trees, but I don't see any end in sight yet. And today I want to talk about lattices of trees. I'm actually going to sit down and talk about it because I find out that they've got a neat camera up there in the ceiling, and I can use that to show you a bunch of stuff that as we're going. So let's see. You can see me there. Maybe they can also project on the screen behind me. I'm not going to need. Yeah. Okay. So, which is the monitor that actually corresponds to? This is the one that's. This is the one that you're seeing. Okay, so a lattice. First of all, how many people know what a lattice is? One person, two people. Okay, yeah. Except that there's at least two meanings of a lattice. There's two completely different meanings of a lattice. In mathematics even, and one class of people who I think about lattices, they think of it as integer points or something geometrical, and those people are probably attending another lecture right now because I'm competing with Gene Golub at the moment. Anyway, integer lattices are really interesting, and that's another topic. But lattices that we're talking about today are the kind that logicians like better, and these are the ones that are about they occur in mathematics when they're talking about an algebraic system called a lattice, and here's the idea. It's mainly based on the idea of ordering between objects. In this case, between trees. So we're going to have a partial ordering. Is any transitive relation. So we can say that that something precedes something else. Let's say, and that's a partial ordering. It's often written like this, and maybe precedes or equals. And it just means that if x precedes y and y precedes z, then x also precedes z. But then it also has greatest lower bounds between any two objects. And these are called the meet of the objects. And so and it's often written x with a little wedge y, and this means that this is the largest thing that is, the largest thing that precedes x and precedes y both. And if there is such a greatest lower bound, it means that anything that precedes x and y has to precede x meet y. And it also has the least upper bound on the opposite side, which is called the join, x with this symbol, y, and this is the same idea. Anything that's greater than both x and y with respect to the partial ordering has to be greater than the least upper bound, greater than or equal to. Now, So this is the idea of the of a lattice, and there are partial orderings all over the place when we want to compare one object to another and say that that one is somehow dominates the other. Many times this partial ordering also is a lattice, means that it has greatest lower bound, least upper bound. Algebraically, it's equivalent to saying that we have these two operations, meet and join, and they satisfy the idempotent law, x meet x equals x, and also x join x is x. And then it has its commutative law, so x meet y equals y meet x, and the same idea, changing all meets to joins. It's associative, and also one more thing, it's absorptive, and this is the thing that so both meet and join are commutative, associative, idempotent. Also, it's absorptive, which means that if you take the meet of x with x join with y, you get x. And similarly, if you take the join of x with the meet of x and y, you get x. This is so now algebraically, if you take any system that satisfies these axioms, you also can define a partial ordering, and this turns out to be the greatest lower bound, least upper bound. Well, this is all abstract, so I want to get into concrete stuff. And today we're talking about lattices of trees. So we want to find partial ordering on trees, so that we can say that if you have two trees, there's a meet of these two trees, and there's a join of these two trees, which means it's the largest thing that is less than both trees, or the smallest thing that's greater than both trees, according to this ordering that we have. And so we're going to be able to take two trees and say that one is somehow bigger than another, or something. Now, actually, but the two trees are going to have the same number of nodes, the same number of vertices in the tree. And so what I want to talk about is actually three different ways to define the concept of order on trees with the same size. But we'll be able to say that one tree is somehow, shapelier than another, whatever. Some idea of the ordering on the trees. And actually, I'm not going to. And actually, I'm going to talk about forest instead of trees. Now, a forest is a bunch of trees, and in fact, we're talking ordered forest. So I'm saying a forest. I got a random forest which I found by my computer on Saturday. I wanted a random example, so I used pi, and I figured out how to find a particular forest with 10 nodes. And so here I'm going to number the nodes in the forest A, B. I'm going to name them A, B, C, D, E, F, G, H, I, J, because there are 10 nodes. And I also am arranging them so that the names of these nodes come out in what we call pre-order of the forest. Pre-order is the same order as like the order of succession to the throne. So if these were the people who were part of British royalty or something like this, this would be the queen or whoever occupies the throne now, and this would be if this person dies, then this one would be next, and if that person dies, this one would be next, and then their firstborn, and then that person's child, and then their firstborn, secondborn. But if all of these are dead, then then this guy comes in, and then we go actually to another line. If you ever saw Alec Guinness movie, where he actually systematically kills all the people that were ahead of him, you understand this. You understand this principle. Now, okay, so this is a forest, and it means it's an ordered set of trees, and in each family the children are also ordered too, firstborn, secondborn. Now, actually, a tree would be a case where there's only one. But you can always think of a forest as if it were a tree, because you can imagine that there's some parent out at the top who has A and I as the two children. And so a forest plus one node is a tree. And conversely, a tree minus its root node is a forest. So I'm going to work on forests. It turns out to be a little bit nicer because the root node is always there. So I don't have to draw it if I consider forests instead of trees. Now I'm going to talk about 3 different lattices on trees, and one of the lattices is invented by Frenchman named, and I can't pronounce it correctly. If there are any French here, you can tell me, but I'm going to say Crusier, Germain Crusier, and this is 1972. Then there's another one which was invented by Tamari in his PhD thesis in Paris in 1954. And then there's a third lattice on forests, which was by Richard Stanley, and this was published in 1975. So these are kind of natural ways to define, as we'll see, to define ordering on trees that also turn out to give us a lattice. Now, the fact that there's so many different ways to get a lattice off of trees is a little bit confusing because Tamari lattice was sort of got famous as being a lattice about trees, and so when people came up with were studying trees and they found some ordering that had the lattice properties, they thought they must have the Tamari lattice. But in fact, I know of several cases where people had the Stanley lattice and they thought they were dealing with the Tamari lattice and so on. Now Crusier didn't actually talk specifically about forests or trees. He had a different way of thinking about it, but it's isomorphic. He really would have talked about forests if he had, if he'd been a computer scientist. But this is what he was talking about is equivalent to forests. And I'll show you Crusier's order first, and it's this. So the first of all, we have the Crusier lattice, and this says, and we have to define a partial ordering between two forests. So we say that F is Crusier less than or equal to G. This is my symbol here for Crusier less than or equal. This will mean that if X and Y are siblings, members of the same family in G, then they also in X, in F, then they're also siblings in F. Okay, they are also siblings in F. So in other words, it's all based on who are the members of the same family of the same generation. So in this case, for example, the sibling, B has no siblings, C has no siblings, is only child. D and H are siblings, E is only child, F and G are siblings. A and I are considered siblings because they're roots of the two trees, and we imagine that there's some parent out there who has A and I. So A and I are considered siblings. So if we look at the nodes, we don't really have to have labels on these nodes. This A, B, C. I'm just doing this for convenience so I can talk about a node. But actually, A is always the node that's first in pre-order. B is always the node that's second in pre-order. C is always the third, and so on. So what it says that anything that if the third and eighth nodes in pre-order are siblings in G, then in F also the third and eighth nodes should be siblings. And I can show you the way Crusier himself drew this lattice. So it's conventional. It's conventional to have a lattice diagram where we put the smallest element at the bottom and the largest element up at the top. And he was listing here only the families, the siblings, A, B, C, D. Here he has A, B, C, D. That means B and C are siblings. A and D are not connected to them, and so on. So if you count up, there's 14 different ways to 14 different points in his diagram here, and it goes up if the sibling is in the subset relation. Actually, this relation turns out that that this is by the ordering that he defined it, he actually reversed G and F here. I'm going to actually do it upside down, and the reason will be clear in a minute. But this is from Cruis's actual paper of 1972. Now, but so here B and D are together. So this will be connected to the ones up above where B and D are still together. And so that's the idea. It's a very simple idea, and there are 14 different forests possible on 4 points. Now, however, I don't. I'm a little unhappy about his diagram because it doesn't show the symmetry of the situation. I mean, actually, I'm starting to. When I write books, and I give a diagram, and there's some way to rearrange the points of the diagram so that there will be a more symmetrical pattern. I think that's more informative, and there's 6 factorial ways to rearrange these guys given these, and some of those are going to look more symmetrical than the others, and you can see patterns better. So I've redrawn. Here's another. This is another paper on the Cruiser lattice that came out just 3 years ago. And again, they drew it a little different, but it's still they didn't show symmetry. So I'm going to draw the lattice symmetrical way. Here's my favorite way to draw that Cruiser lattice for forests on 4 points, and it's symmetrical. Mine is symmetrical, believe it or not, in the sense that if you turn it this way, you get the same. The red lines are the same, the lines between. So there is this kind of a flip operation that says that the lattice from the bottom up is the same and it looks the same as the top down. So it was okay for me to change it. But the main reason the reason I changed the order so that what he called the bottom was for me the top, because it's conventional to call the top element of a lattice 1. And this forest just looks a lot more like 1 than the other one. I hated to see that 1 sitting at the bottom. See, so I flipped it over. Now, it's so I could have, if you like a definition that has F first instead of G, I could have said if X and Y are not siblings in F, then they're not siblings in G, and that's an equivalent definition. It's the contrapositive of this. But anyway, that's the. Now, so here we have. Here you can see a forest, for example, up at the top. This one. So if let's see, what am I saying? I defined it, if they're siblings in the big one, then they're siblings in the small one. So certainly this guy is bigger than everything else because this doesn't have any siblings at all, so it's no condition. And this one is smaller because everybody is together there. So here we have a case where A and C are siblings, B and D are not, because in this particular case, B is a child of A and D is so A and C are siblings. So the ones that come underneath that, A and C are still siblings. This guy and this guy, A, B, and C. The only ways. Okay, so that's the Cruiser lattice, and we can then also say that this is equivalent to saying that G is reverse Cruiser of F. Actually, I would make this K in a light font so that it would look like a symbol instead of a letter, and then you can take according to this lattice let this be the meat of F and G, and this would be the greatest lower bound, and this would be the join, will be written this way. So it's just an ordinary meet and join symbol, but with this extra line on there to remember that we've got to distinguish Cruiser from Tamari and Stanley in this because we're going to have many lattices on the same guys, on the same forest. Okay, so that's the definition. Now let's try to analyze something about it. So the main thing that we want to in a finite lattice, the important thing is what they call covering, and this means that one forest covers another, it means that it's less than the other, but there's nothing in between. I mean, the transitive law holds. So if F is less than G is less than H, then F is less than H. But then H doesn't cover F. The things that cover F are the things that are just bigger than F, but not any. There's nobody in between. And in a finite lattice, you can then find the ones that directly precede. And the red lines in this diagram are the ones that cover, that show what covers what. So this would go to here, and then that would go to there. So this is less than this. What does covering look like in the Cruiser lattice? Well, let's suppose we have some kind of a forest and some part of a tree within the forest. So here's for example, we might have somebody has 5 descendants, and whatever their names are, and then they have some tree below them, and then there might also be, this guy might also have siblings on either side, and might be a descendant of other things, but somehow we're looking at a part of a big forest, so there's some environment to this situation, and then I'm going to amputate this diagram, and I'm going to move, let's say part of it, let's say these two. I can take 1 or 2 or any number, except I can't remove the left child of the family, and I fasten those two below the one that was just to their left. Now this is an example of covering. I'm not sure if it goes to meet or join. I kept flipping this diagram upside down, back and forth. But I'll put an arrow here. So imagine imagine this operation. You have some huge forest. You go into one of the families of the forest. You pick out some adjacent people, not at the left end, and you pull them down and attach them at the very end of the sibling to the right. Now, at the very end, what I mean is whoever is last in the pre-order, in the brother here, in this guy, or the sibling, this guy, then if we look at one order, there's going to be somebody who's last, and then the pre-order will flip over to this tree, so that person will be somebody childless, and so we can give them a family now. So we can take these and move them down and put them on, and attach them to this other place. And by the way, a node in a forest that has no children is called a leaf. And so what we've done here is actually we've reduced the number of leaves by 1, because all the leaves that were in these trees are still there, except for the rightmost guy in this branch. So by moving this down, I decrease the number of leaves, but I preserve the pre-order. I preserve the order of succession to the throne, because everybody here still is going to come in the same order that they had before. And what changes have I made to families? Well, here we have these 5 people were siblings, and here 3 of them are still siblings, and these other 2 are still siblings. So it turns out that everybody who was siblings down here is still siblings up here. So this must be actually the thing at higher up in the tree. And if we look at that lattice now, we should see then, if we rank things, we start out with 1 leaf, 2 leaves, 3 leaves, 4 leaves. So the level that you're at in the Cruiser lattice is the number of leaves in the forest. And so if you're two forests that have the same number of leaves, there's no way that one is going to be ordered from the other one according to the Cruiser method. That's an idea. Now, next thing I want to tell you about is duality, and this is the idea of flipping over the diagram so that it's going to look the same the other way. So it says that every forest is going to correspond to another forest that's the dual of that forest. It's somehow the upside down forest. And I will take this example and make its dual, and we'll write it down. So we'll call this F, and then I'm going to have the dual, and I'm going to call that the reverse of F, and I'll write that to the right. I'm going to show you how we do it. Now, the way that I'm going to do it is a little bit strange, but it works, and so that's why I do it that way. And there are several other ways, but this is the one that turned out to lead to all kinds of properties that, in fact, most of what I'm saying today is new. I mean, it hasn't been published, and it was surprising to Stanley when I told him at MIT and so on, and other people who work in this area. And I don't have time to write a paper about it right now, so pay attention. Although this is being videotaped, I guess. But now, so what we're going to do is I'm going to write I'm going to represent the forest first as a binary tree, and I'm putting siblings together backwards from the normal way. I'm saying that the left link in the binary tree is going to point to the sibling to the left, and the right link in the binary tree is going to point to the rightmost child. So I is going to have rightmost child J. J doesn't have anything. A has child B, and B has a rightmost C, and then C has two children. The rightmost is H, and then there's D. And then D has E, and E has G and F. Now, the normal way to represent a forest inside a computer is using the right link for your right child and the left link for your leftmost child. Here I'm using the right link for your rightmost child and the left link for your left sibling. I'm switching the whole thing around. You think that it wouldn't make any difference, but in fact it makes a big difference. And I never realized it until I was doing one of the exercises for the revised Volume 1 earlier this year. And the important thing about the left sibling right child representation instead of the right sibling left child representation is that if you read this binary tree in symmetric order, this is the left to right order, also called in order, it corresponds to the pre-order of the forest. So if I'm reading in symmetric order means you take everything to the left of the root first, and then you take the root, and then you take everything to the right. So everything to the left of the root starts with A, then B, then C, and then I have to do the D, E, F, G, H, I, J. So the symmetric order of this binary tree is the pre-order of the forest. And it doesn't work out so nice when you do the other way. Now I've got this in something that's symmetrical between left and right, so I just flip it. And I go J-I, A, B, C, D, C, H, D, E, G, F, and I just take the mirror image, and now I convert this back and consider this a forest. This is going to be the dual forest. So F reversed is going to have two trees, J and I, whose left child is A, B, C, H has all these children, and H has D, E, and G, and G has F. So that's the reverse of that. That's the dual of that forest. Okay. Now, what good is this? What good is this operation? And the interesting theorem is that if F is Crusier related to G, then G dual is Crusier related to F dual. So that says that you can flip the diagram upside down. The duals, if one is bigger than the other, its dual is smaller. Okay. And so that's this notion of duality. Now, basically you can prove this by induction by looking at the covering relations. You figure out what's the dual of this guy and what's the dual of this guy, and you can see that in the case of the duals, they're going to go this way. We're going to detach something from the dual and move it to the dual of that one. I don't have time to go through the proof, but that's the idea of the proof. Okay, now I told you about the Crusier lattice. I'm going to talk to you next about the Tamari lattice. Tamari lattice was the first lattice of trees that was discovered, and this is the one that I actually was one of my previous Christmas tree lectures was about this Tamari lattice. It was I call that the associative law, and we studied we said that one tree could be changed into another tree by what computer scientists call a rotation operation on a tree, and it's equivalent algebraically to applying the associative law in a formula, changing AB quantity AB times C into A times quantity BC. However, I'm not going to. That was the way Tamari defined his lattice, but it turns out that there's another way, in some ways maybe nicer, to define a Tamari lattice, which I'm going to which corresponds very directly to one of the ways that people have been for 30 years, almost 40 years now, representing forests inside a computer. In fact, instead of calling them forests, they call them COBOL data division, and the representation and the COBOL compiler writers in 1960 found that the best way to represent COBOL structures was in terms of something that's very close to the way I'm going to define a Tamari lattice for you now. So here we have the second thing is the Tamari lattice. And I'm going to say that F is Tamari related to G. This is going to mean, by definition, that the number of descendants of X in F is less than or equal to the number of descendants of X in G for all X. In other words, the first node in preorder of F has fewer descendants than the first node of preorder in G, and so on. So it's all based on knowing the number of descendants of every node in the forest. Now let's let me go to our example forest here, and let's figure out how many descendants everybody has here. So A, B, C, D, E, F, G, H, I, J. So A has, I'm talking proper descendants, so there's 1, 2, 3, 4, 5, 6, 7. So A has 7 descendants. B has 1, 2, 3, well, 6. C has 1, 2, 3, 4, 5. D has 3. E has 2. F and G, none. H, none. I, 1. J, 0. So I have this coordinate system 76532 that's another way to describe the structure of this forest. It turns out from these numbers I can reconstruct F, and let me show you how to do that. So inside of a computer trying to represent a forest or hierarchical type of relation. And I put these numbers here, 7, let's put them up high, 7, 6, 5. These are called the scope of the node. It's the number of descendants it has. It's how far the influence extends in preorder to the right. So I've listed the names of the nodes in this preorder. And now A has a scope of 7. So we go 1, 2, 3, 4, 5, 6, 7, and say these guys are all descendants of A. These guys are all descendants of B. C has these. D comes here. It comes here. I should have left myself more room. I hasn't. Okay. So this tells you where the families end. So it's obvious then. A has B as a child, and then B has C as a child, and then C has D as a child, D and E and and E has F and G, but E doesn't have H, so it must go back to somebody who had the scope here that was C. So that's the way it reconstructs, and I has J. So these coordinates are equivalent to the structure. It's a numerical way to represent the structure. And the rules say, and not every sequence of numbers is going to be a set of coordinates in this way. Do you see which ones are going to be the ones that are okay are the ones where these lines never cross. The coordinates are bad if you have if somebody here would say 6 and then it goes over 1 2 3 4 5 6 and then somebody here would say maybe 3 and that would extend out here. Because this guy can't have descendants that aren't also your descendants. All right. So that turns out to be necessary and sufficient condition that if you draw these scope links like this, that they aren't going to cross over each other. Now, it's real easy to tell then in a Tamari lattice whether or not one force is related to another. You just look at their scopes at these coordinates, and you compare one at a time. Each one has to be less than or equal to the corresponding one in the other side. That's the idea of a Tamari lattice. Now, first theorem is be the same as what we had before, that the duality still applies. So F and G, if and only if the dual of G is Tamari related to the dual of F. Now, that's obvious because what I've done here is I have changed left and right. Okay, the symmetric order is symmetrical between left and right, and so what's actually happening here, if I let me see. Do I have to talk about covering first? Maybe. I guess maybe I need covering in order to. Yeah, I got to explain covering in order to show you why this theorem is obvious. But let me give the coordinates of the dual anyway. So the dual, in the dual, I'm going to give the coordinates in pre-order again. So I'm going to call it J, I, H, G, F, E, D, C, B, A. And so J has no descendants. I has 1, 2, 3, 4, 5, 6, 7, 8. H has 4. G has 1. E, F has none. E, D none. C, B, A none. So the dual of this coordinates are these coordinates. And actually, I don't know any easier way to. I don't know any easier way to describe this except by this binary tree representation. Take the forest, and well, I know how to go from the scope links to a binary tree, and then I flip the binary tree over, and then I can figure out the scopes again. But this is a theorem, but I present it ahead of time, so I got to talk about the covering in the Tamari lattice. When is it? What are the relations? So let me first show you a picture of the Tamari lattice, and one of the pictures is here. It's kind of a mess, but I'll clean it up later. The main thing I want to show you in the picture is that I've got these same 14 forests written down here as before, but I've also now added in blue these numbers. These are the Tamari coordinates, and to tell when something is Tamari less than another, it means that coordinate-wise it's less. So the 0, 0, 0 is going to be less than everything. Here's this 2,000 is going to be less than 2,100, and it's less than 3,100 too. But that's not a covering relation. So I've shown in red lines again only the covering relation. So 2,100 goes to 3,100, 3,200, 3,210 is the big guy here. A has 3 descendants, B has 2, C has 1. This is the one at the top. So by looking at any two of these trees, by the coordinate systems you can immediately tell where they're related, but the red lines are the covering lines showing you which are something that's just bigger than this. You know, there's nothing between 200 and 3200. And that's obvious if you look at the if you look at this non-crossing condition, because the 200 has a scope going out to here. So if you're going to increase the one in front of it, you're going to have to give it a scope of 3. All right. Well, now I already talked a lot about the Tamari lattice, so I'm not going to repeat what I did in that lecture. But I wanted to. But in the covering, I do want to show you what the covering relation is in the Tamari lattice. And so if we look at the binary tree form of the forest instead of the other form, in a binary tree we have a situation like this. Here's a node. Here's a node. It has 2 subtrees, and this guy has another subtree. Let's call these alpha, beta, and gamma. The number of descendants of this node is I'll call it absolute value of beta. That means the number of nodes in this tree beta. So that's how many descendants this guy has, because to the right is we're listing at the right all of the descendants and to the left sibling. Similarly here, the Tamari coordinate is the number of descendants of this node, which is the size of this tree gamma. Now the Tamari covering relation would take this into there's also an environment. So this is part of a binary tree. It has some attachment to a larger tree, perhaps, either from the right or the left, but it goes up high. So what we do is we rotate it, and after a rotation in a binary tree is one of the it's the most fundamental operation for balancing a binary tree, and it's used in lots of different computer algorithms. Then we have alpha, beta, and gamma. The nodes are still the same in symmetric order. First come all the nodes of alpha, then comes this guy, then all the nodes of beta, then comes this guy, then all the nodes of gamma. Same on this side. It's alpha, this. But now, notice what's happened. This guy still has gamma. The size of gamma is the Tamari coordinate here, but the Tamari coordinate of this guy is 1 plus the size of beta plus size of gamma, because now that's the size of the right subtree here. So you can see that this operation has increased exactly one of the coordinate of the Tamari coordinates, and it increased it to the smallest possible value. If you took any value smaller than 1 plus beta plus gamma to this guy, it wouldn't satisfy this it would violate this condition. So if I'm going to increase this Tamari coordinate from absolute beta to anything else, it has to be enough to avoid crossing the link from this guy to his children. So basically, by studying this kind of idea, you realize that this is exactly the smallest. This tree is above this one in the Tamari ordering, and there's nothing in between them in the Tamari ordering. And furthermore, all of the coverings are of this kind. So the covering relations are formed that way. Well, now what's happening is that if I flip left and right to take the dual of the operation, then we have different coordinates because now we're counting the size of the left subtrees instead of the size of the right subtrees in the coordinates if I'm flipping left to right. So what must happen is that the operation of on the dual must be taking the dual coordinates, and every time I do a positive rotation, I'm sort of doing a negative rotation on the dual. So the conclusion is that if every covering relation in the Tamari lattice increases the positive coordinates, and in the dual it decreases it because it'll go from something like this to something like this if you flip left and right. therefore, on the covering relations, the dual of this is less than the dual of this. If this is less than this, so flipping left and right, this is going to be less than this, because flipping left and right also converts this side to this side. That's why I had the theorem that I mentioned a minute ago, that the duality is reversed. So again, this diagram, if I tipped it on its side, the red lines would be in the same position, because what I've done is I put the dual of this guy over here and the dual of this guy over here. These are I worked everything out so that their dual was in the 180-degree rotation position of the other person. So now there's another thing I wanted to show you about this picture, though, and that is the next theorem, which is why I like this way of representing the force, and that is that if F is related to G in the Crucier lattice, then F is also related to G in the Tamari lattice. So these lattices aren't independent of each other, but there's a strong connection between them. So what does that mean? Picture-wise, it says that anybody who any relation in the Crucier lattice also corresponds to the same relation in, like here. This tree has to be less than this one. Well, this tree is less than this one. It isn't directly less than this one, but it's less than this, which is less than this one in the Tamari lattice. And so that's the theorem that relates one to the other. It says that being Crucier related is a stronger condition than being Tamari related, but they are exactly analogous. That this is a little coarser relation. And this theorem is also obvious because if you look at the covering in the Crucier lattice, what we've done, if I can only find the picture of the covering in the Crucier lattice, we've done something that increases the coordinates. Yeah. So if we look at the Tamari coordinates, how many descendants everybody has here? This was the guy that has this is the big guy and this is the small guy, and you see that the number of descendants of everybody here is the same, except that all the people on this right path here have gotten more descendants than they had here. So all of the Tamari coordinates of some of these nodes are bigger than they were up here. But inside the rest of the diagram, the Tamari coordinates haven't changed. So by going from here to here, I increase some Tamari coordinates. I don't decrease any Tamari coordinates, and that's why it's less than the other one in Tamari land, because Tamari definition is based on the coordinates entirely. Okay. So now I've got this idea of Tamari lattice, and I promised you 3 lattices. I'm going to the third one, which is the Stanley lattice. Before I do that, let me just mention, why do we study these things? I mean, the theorems turn out to be rather beautiful when you start looking at them on trees, but so what? And I don't know. Years ago, I wouldn't even have raised that question, because it was, to me, it was so obvious that it's interesting to discuss this stuff that I didn't mention any other justification. But anyway, so some people now think the only purpose of computer science is to make money for other people. So how does this make money for anybody else? And so my answer to that is, well, historically, it's always turned out that whenever there's a clean mathematical relation between fundamental objects that we work with every day, like trees, forests, this turns out to give us more familiarity with those objects. And we study these things, we look at them, and all of a sudden we're more comfortable with trees, and we see bigger bigger pictures. We take giant steps when we start thinking about trees. We're able to envision many more things to do with them. We think of other structures that are built on top of these, and it's because we've gotten some fluency. In the old days, we didn't have the name of what a mathematical concept of a tree was, and neither do we have names for other things that we now use every day, like vectors and fields and lattices. So by studying these properties of these things, especially when they're clean and natural, it always has turned out that this has led to later developments in the next generation. So it's there's another lattice on permutations. It's turned out that it was first discovered by some scientists about 1960. And I did a search for it, and there's been hundreds of papers on this written since then, where people have found all kinds of ways to use that lattice, which is now called the Bruja lattice. But anyway, there's so many people finding important ideas of this lattice. I've related it to sorting networks and all kinds of things that weren't clear originally why they would be important. But when there's something clean and natural like this, it always seems history always makes it important. So that's why I think this is cool stuff. Okay, now the Stanley lattice, and here I could instead of using an S, I'm just going to use the ordinary subset notation because it looks a little bit like an S. And then I can use for the opposite relation, I could also say G is related to F like this, and the meat can be written this way, and the join can be written this way. So I have symbols for it. And for Stanley lattice, I'll just use ordinary set symbols, meat, cup, and cap. So anyway, what does this mean? And this says simply that the depth of X in F is less than or equal to the depth of X in G for all X. In the same way, so here we have coordinates of a forest that are different from the Tamari coordinates. The Tamari coordinates, we listed how many descendants everybody had. I don't have another color of pen, so I'm just going to write these. So these are the Tamari coordinates. The Stanley coordinates in this forest are the depth of a node. So A is at depth 0, B is at depth 1, C is at depth 2, D is at depth 3. See what I'm doing? How far down did I go? E is 4, F and G are at 5, H is 1, 2, 3, I is 0, J is 1. Okay, and in the dual I can show its depth too. So J was 0, I is 0, H 1, G is 2. Just write them down: 3, 2, 2, 1, 1, 1. Okay, now, so to compare two things according to Stanley ordering, we just compare component-wise to see whether their coordinates are related. The first one is always 0. The next one would have to be less than or equal. There's a very simple way to get from the t coordinates to the s coordinates, or back again. Can anyone see that? First of all, I'll give you a clue. The sum of the t coordinates equals the sum of the s coordinates. That's called the path length of the forest, because the sum of the s's is the sum of the distances to the root, and that's what we use in so many applications, called the path length. It corresponds in a computer algorithm. It corresponds to the number of times we have to process things. So path length is important in many applications. Also, it's also the number of descendants of A plus the number of descendants of B, because the number of things that come through A is the number of descendants of A, and the number of things that come through B is the number of descendants of A. Okay, so do you see how to get from the one to the other? And the answer is, let me take the Tamari coordinates 7, 6, 5, 3, 2, and for the 7 I will convert that to 0, 1, 1, 1, 1, 1, 1, 1. I put 7 ones down. For the 6 I put down 6 ones. For the 5, I put down 5 ones. For the 3, I put down 3 ones. For the 2, I put down 2 ones. And for this, the ij, I put in another one. I add these all together, and I get 0, 1, 2, 3, 4, 5, 5, 3, 0, 1. Those are the Stanley coordinates. Okay? So in other words, just having 7 descendants means that you're going to increase the level of all these next 7 guys by 1. All right? So you can easily get from one set of coordinates to the other. That means that the next theorem is obvious. If F is Tamari related to G, then F is Stanley related to G. Because you see, if F is Tamari related to G, that means that F's coordinates are component-wise less than or equal to G's coordinate. So if so then there are going to be lower bounds for the coordinates that you get for Stanley. Everything I add, this. If I change this 7 to an 8, I would bring a 1 here that would increase the Stanley coordinate by 1. If I change any of these numbers and make them bigger, I increase the sum. So that's the relation that similar to what we showed. You see the Crusier relation implied the Tamari relation. Now the Tamari relation implies the Stanley relation. So now that means that we should be able to take take a look at the Stanley lattice. Here's the Stanley lattice, and people who study lattices will recognize immediately that this lattice is nice. It's called a distributive lattice. Distributive lattice is where these operations meet and join not only satisfy the commutative, associative, absorption, and so on laws, but they also satisfy the distributive law. X meet Y join Z is equal to X meet Y joined with X meet Z, and the other distributive law as well. Distributive lattices, when you look at them, tend to look like cubes and grids and things like that. At least the small examples, and they have a definite structure made out of little cells, and other properties besides. But anyway, so this lattice meet and joins in the Stanley lattice also satisfy the distributive law, and the reason is simple, because the Stanley coordinates, we have to say what are the legal sequences of Stanley coordinates. What sequences of integers are going to describe the Stanley coordinates of a forest? And the rule is that that a sequence S1, S2, Sn is a Stanley coordinates sequence if and only if S1 is 0 and Si plus 1 is less than or equal Si plus 1. As you go from left to right, you start with 0, and then each one is at most 1 higher than the previous. I guess we have to lower bound it. So after a 0, I can go to 0 or 1. After 1, I can go as much up to 2. After the 5, I could have gone to 6, but I picked the 5. Here I could go as high as 6. But that's if and only if. So now if you have if T1 through Tn is also a Stanley sequence of coordinates, then S1 the minimum of S1 and T1 through the minimum of S1 through Tn, and the maximum, if I use these operations for min and max, are also going to be Stanley, because the maximum of Si plus 1 and Ti plus 1 is going to be less than or equal to the max of this plus 1. So, and similarly with min. So this operation on coordinates makes it easy to take the you just take min and max on the coordinates, and you get the Stanley upper bound and lower bound, and that's why this is a distributive lattice. If I take the Tamari lattice,
mention the min and max.
What?
You should mention the min and max.
Min and max are distributive. Yes. Min and max define a lattice on the integers min and max define a distributive lattice that looks like this. I mean, the lattice diagram is like this, which is a distributive lattice indeed. But it's somehow the simplest. In fact, I have another theorem that I could embed all the forests into a lattice that has this structure, just by lexicographic order, say, of the Stanley coordinates. And so then one thing less than another would, if something less Stanley-wise would also be less in this. This lattice would have 14 levels, 14 trees. Well, here I've taken the Stanley coordinates, I've converted them to Tamari coordinates, the equivalent Tamari coordinates, and put the things in the same place, and drawn again the covering relations in the Tamari lattice. Well, these are the covering relations in the Stanley lattice, and this is an illustration of my theorem that says that if F is related to G by Tamari, meaning that if I take any one of these red lines here, then that's going to correspond to some path in the Stanley lattice. This one is less than this, and the Stanley lattice will have a path from there to there. So here again, this shows that the Tamari lattice somehow gives you more information than the Stanley lattice, but the Stanley lattice is nicer because it's distributive, so it has this. Now I've never seen. This was all a strange concept to me, to have several lattices on the same point. I've seen studies where people take a lattice and then they identify clusters of its points, and they get congruous lattices. They get other kind of, but I haven't. I'm not sure. I don't even know what the name for the concept is. It's not. This isn't a subset of this lattice. I think I can say it's embedded in the lattice. It has, but I'm not sure what the right. But it's happening in these lattices. So I'm going to have to get more familiar with the concept. One of the corollaries of this is, for example, that the meat in the Tamari lattice would have to be contained in the meat in the Stanley lattice. Because you see, F meet G in the Stanley lattice is the greatest lower bound in the Stanley lattice, and so, the greatest lower bound of F and G. But F meet G in the Tamari lattice is a lower bound on F, and it's a lower bound on G, and so it has to be less than the greatest lower bound. So looking at it in the Stanley lattice, we're going to have this relation. Okay.
Quick question?
Yeah.
Look like shortcuts?
What?
One look like the shortcuts of the other?
One like
Taking shortcuts, you know?
Yeah, that's right. Yeah, it says that there's a whenever I have a covering here, I mean covering here, then I have a chain here. So yeah, this is a shortcut lattice, and similarly, if I went to the Crusier lattice and went back to that, there would be shortcuts there because the Crusier lattice had only 3 steps from the bottom to the top. By the way, the Crusier lattice, the levels in the Crusier lattice were the number of leaves, if you remember, and leaves are easily seen in the because the leaf means no descendants, so that's the number of zeros. And so if you look at here, you can see how many leaves. So you look how many zeros there are, and you can see how. I've got some cases with 2 zeros up rather high here, but these would still be in the second. These would. Sorry, there's always 1 zero anyway. The number of zeros anyway tells you the level in the Crusier but there's still more information as to in the Crusier lattice as to who's contained in who. Now this picture isn't very intuitive. Here I was saying before, when you draw a picture of a lattice, you want to have some diagram that explains what it is. Here are the 14 forests on 4 points, and I want to find a way to draw them. What time is it, by the way? I don't have a
20 past 4.
20 past 5. Okay, so I gotta start speeding up here. Anyway, I gotta get to the interesting problem that I want to tell you about. So here, for example, is a paper that came out a few years ago. It shows that lattice again. It's not really. It's a little bit cleaner than in my drawing, you know. But there it is. Here they described it not in terms of forest, but in terms of an equivalent concept of dividing a polygon into triangles. And those again, that follows the Tamari lattice. Here's another picture by Markowski. Again, he has a picture of the Tamari lattice, but you know it doesn't look appealing. Now, so I tried to figure out what this was, and a year ago I gave a talk at Berkeley at the graph drawing conference, and I wasn't talking about the Tamari lattice, but just the connectivity, the things that you can get from when you take two trees. What two trees are adjacent if you can get from one to another by a rotation, and so all of these covering relations in Tamari lattice correspond to rotation. So ignore the top-down part of it, but just look at the connectivity between these things and say, how could I draw that in a nicer way? And I'm thinking about this. Here I want to show. This is for the first time I'm showing publicly a page from the new edition of Volume 3 of The Art of Computer Programming, which I hope to send to the publishers next month. I'm still working on it, but anyway, here's a picture. It's still was also in the previous edition, not quite as beautiful. And this shows a different lattice. This is a lattice on permutations, where it's the inversion lattice of permutations. That one permutation is less than another if its inversions are a subset of the inversions of the other. And here, notice that we can also see this as if it was in 3 dimensions. And it's called a truncated octahedron. And you get it from taking an octahedron and lop off some of the vertices, and you get this interesting shape that has hexagon faces and square faces. Well, I wanted to do this. People call this also the permutahedron because it's a polyhedron that's based on permutation. And the Tamari lattice has been called the associahedron because it turns out that people have found a way to define a polygon whose faces and vertices and edges correspond to the structure of applications of the associative law. So in my talk at Berkeley to the graph drawing thing, I took the Tamari lattice and I tried to draw it the best way I could, applying some principles that I was talking about there. And this was my best shot at it afterward. And it started to look a little bit like, you know, like something that you can have in the you know. Oh, for goodness sake, I left it upstairs. I had a model that I wanted to show you. Oh, how terrible. Well, now, yesterday I decided, let's look at this thing. This has 6 faces that are pentagons, 1, 2, 3, and then underneath the three things on the back are pentagons, and then it has 3 that are squares, and you know, or at least quadrilaterals. 4-sided. So I said, well, let me try to build one of these. So I took out some scissors and I cut 6 hexagons, pentagons. I mean, and I made them regular pentagons, and I pasted them around, and I got something that I tried to draw today, and this was the best I could do. But it looks sort of like what I got, and it was actually a very appealing little thing. And I'm sorry I left it on. Going to be one of the highlights of my talk to show it to you on camera here. But anyway, this almost gives you the idea. Now, so what I did here is I took 6 pentagons and I wrapped them together in this pattern, and then identify the vertices with their Tamari coordinates here, and connect 2 things that are connected by a rotation. Now, I'm not sure this is really a legitimate solid. I haven't worked out that it might be that. I mean, I'm sure that these pentagons hook together this way, but I'm not sure that these places where you get 4 points here, I'm not sure that those are all in the same plane. Maybe that was why I was having trouble trying to sketch it, you know, because I built it out of paper, and my scissors was, and I didn't take much care. I just sort of traced out what looked like a regular, you know, so I could fudge it a little. But okay, but even so, something very close to this is actually, you know, maybe the pentagons aren't going to be regular, but you get a shape like this in the following way. you take two tetrahedrons and you paste them and you glue them together, so that now where two of the faces are just on top of each other. So now what you have left is a hexahedron. It has three from one tetrahedron and three from the other, and it's been glued together. So it has three vertices where they were glued together, and two other vertices that used to be the top of each pyramid, of each little tetrahedron. So you got this thing with 5 vertices and 6 faces. Now you take the 3 vertices in the middle and you cut each of them off. That converts that vertex into 4 vertices, because that's how much is surrounding it. And so you've added 3 plus 3 plus 3 vertices, and you've gone from 5 vertices to 14 vertices, which is this thing. So here, if you imagine these 4 things were shrunk to a point, and these 4 were shrunk to a point, you'd get this hexahedron, this thing that has 2 tetrahedrons put together. And so now what I'm doing is say take your hexahedron and try to chop it off at the thing that's most aesthetically pleasing. Don't make these squares too small. Don't make them too big, but make them so that it looks nice. And maybe it'll be, so I couldn't find in any books this figure made out of pentagons and squares, and so it probably doesn't exist.
Well, it's not.
What?
It's none.
It's
The
no?
construction you just described.
Is no. Okay, so I don't know any references, but now here's my question, and that is, first to find the most, I would like to people using nice 3-dimensional drawing tools and so on, to find me the best visualization of a real truncated hexahedron, and you find the view that makes it best, so that you have room to draw in the labels, these coordinates and things like this, so that you can write a nice textbook. And furthermore, you have to position it, if possible, so that it respects the lattice ordering. Here I didn't respect the lattice ordering. This 3, 2, 1, 0 is the top element here. 0. So I have to tip this guy in such a way that gravity also corresponds to making the Tamari coordinates bigger. Is that possible? I leave that as an interesting open problem. Here's my best diagram of the Tamari lattice right now, and it doesn't, it satisfies the gravity condition, and it looks a little bit intuitive, but I would much prefer something that looks like the one we have for permutations, if somebody can think of one. So I can't show you the other beautiful things I wanted to show. For example, the number of paths in the Crucier lattice, the number of ways to go through from the bottom to the top of the Crucier lattice on n things turns out to be exactly n to the n minus 2. And the beautiful one-to-one correspondence between that and several other things like parking functions that I talked about in my previous talk. But one thing I got to mention just at the end is that an hour before I gave this lecture, I learned about yet another lattice on forests that has just been discovered, and I'm going to call it the Andrews lattice. And he actually doesn't describe it in terms of a lattice at all, but Richard Stanley, by studying the details and thinking about it a while, was able to realize that he's really getting a distributive lattice out of this. And here's a picture of it on four elements. And it's again a way to describe things by terms of coordinates, and you compare things coordinate by coordinate. So here's I did this just 15 minutes before today, so I haven't absorbed what the Andrews lattice is yet. But it's if somebody wants to look at it, I'll be glad to talk to you about it, because I wouldn't at all be surprised if there wasn't a way to map the Stanley lattice so that anything that's Stanley related is also going to be Andrews related, and we get yet another because this seems to be yet another natural way to define relations on forests that turns out to be distributive and has elegant properties. So this indicates that there's still looks like there's plenty of stuff to be done. I had even a few more open problems. So I guess maybe next Christmas or the Christmas after that, or one of the ones in the future, I can again return to the topic of lattices on trees and tell people about still more things that happen to be true about our beloved objects of trees and forests. Thanks a lot. Question?
Is there a concept you're trying to capture?